We are back. Hold on. There's my window. There we go. We're back. Time for science. Let me make sure I haven't missed anything on the Discord. And also I'm not muted. Good. Huh? Okay. Huh. 1%. Cool. Captain's done some nice optimization. Up to 200K. That's getting to a respectable speed. It's my restream. Okay. So what we're going to do now is go back to the hyperparameter tuning stuff. And it's going to take me a second to get back into this. This is going to be a little hard. This is a combination of fixing messy code and hard math. So I think I was looking at the acquisition function. What is Ymax? The regular expected improvement. Okay, so they're saying that this one is expected improvement over whichever Pareto value is sampled, and this is expected improvement over the best Pareto value. And they want to balance. They want to improve the best ones. Empirically, this only samples the highest performing part of the Pareto front. And EIPF only rarely, yes. Our solution is to sample a threshold cost from a log uniform distribution. Okay, that's sketchy because, I mean, I guess if cost is perf in seconds, then yeah, that is log distributed. So you sample from log space, and then you evaluate the Pareto front performance there. So this gives you a comparison. Okay, perfect. So we also note the version that always uses the maximum, no Pareto, does not sample. The version that always uses the max, no Pareto, This is higher mean. What the fuck? It's got a bigger spread, but... Well, this... The thing is, the Pareto thing that they're doing actually makes sense, so I assume it's the other choices that they've made that have screwed with this. Figure 5. Oh, they actually have a comparison to Hebo. Perfect. Here's Hebo. And there's the... Okay, so here, this is fine. This is what we're interested in. So Hebo's over here. They don't have, like, random search and stuff on here, which they should have. Asha is way better? What? Asynchronous successive halving. Wait, this does better than them? Let's see. And for some reason, they do way worse over here. And carbs is like... Dude, what the hell is wrong with this? They... Except on image classification, they underperform Asha. Something screwy. I mean, this could literally be like the way that search spaces are set up and stuff, though. What is this? We might have to implement this if it's simple. Allocate a small budget to each configuration. Allocate a small budget to each configuration. Evaluate all configurations. Increase budget configuration until maximum per configuration budget is reached. So you just give it a bunch of... So these are like... You come up with random search config or whatever. You train it for a bit. This is not smart. There's like a really obvious optimization here that they're missing. Wait, is this different? Successive halving. Asynchronous successive halving. Oh, this is just that it's embarrassingly parallel, right? Let me make sure I understand this. If this is a strong baseline against carbs, I want to understand this. So resources so you get the top K. Draw random. Okay, so you keep sampling basically. You have a fixed number of configurations, and you just drop the poor performers. Okay, so that's interesting. I mean, this means it's probably worth, continuing, like, maybe carbs is not going to be the end all be all of this. Though I think that they get pretty darn good results even with all these screw ups in it. That variant of random search kind of does get better over time, come to think of it. Because they sample a bunch of parameters and they keep dropping the bad ones. And then they keep running for longer. There's definitely something to that. It would be a good baseline. It would be a good baseline. And I could implement that pretty easily. So I think that I might, since this seems like the simplest, let me see. Local search start, the set of specified low-cost parameters. Blend search does pretty okay on everything. Hebo. This is a complicated method that Carbs is built on. Carbs underperforms on language modeling, outperforms on RL, and outperforms on image classification. Interesting. TPE is up there as well, though this is weird. This asynchronous halving thing could be pretty decent. Because it is compute adaptive, which I like. And it's trivially parallelizable. I mean, I'm definitely going to need a better benchmark than I currently have. Man. It's crazy that this does so well on the RL. I guess it gets more runs. The thing of the carbs is supposed to be able to do this automatically. You know, I kind of suspect that carbs just isn't tuned correctly, because carbs should do this adaptive compute better than this. So we'll consider this as a baseline in a bit. This would be a good baseline. But for now, let's go back to the math of carbs. Oh, wait, there was one thing I wanted to look, which is the ablations. So full carbs does the best on RL. No burrito really hurts it. No clamping really hurts it, and then no resampling. Okay. Hurts it a little bit. Well, some a lot. So let's see what this is. Figure 6. Cost in hours. Oh, okay, here. So blend search does pretty nicely. Doesn't give you this nice front. It's kind of like spotty. Asha has a very nice one. This is just like straight. Yeah, this is nice. So Hebo and carbs are both the Gaussian process-based ones. You can see here that Asha just does a ton of these really low-cost runs. I don't know how useful these are. But Asha doesn't use a predictive model. So actually for Asha, these are useful, because it's just going to keep the ones that are good. It's not trying to build a predictive model. Okay, that makes sense. What's this no clamping? So no clamping, no Pareto, no resampling. This is probably the no Pareto version, which would make sense. You get this weird distribution. So let me see what they do. Sample a threshold cost. We then evaluate the Pareto front cost there. I'm confused. Noisy. Okay, let's take a look at these first. Output warping. Output variable have approximately Gaussian distribution with zero mean and unit variance. Yeah. Quantile transform. Fine. Resampling. So this doesn't matter in my synthetic test because it's perfectly accurate, but we will look at this. Noisy observations are particularly important to handle correctly for carbs. Best observations are used to define the local search space. Thus, a particularly extreme noise point might prevent the algorithm from finding a better optimum. This is true. 1 out of every n resample suggestions is a set of parameters that has already been observed. We count the samples for each of the existing Pareto front points and suggest parameters which have the smallest number of samples, breaking ties by one by choosing the one with lower cost. Okay, so they're resampling on the Pareto front, but the thing is the Pareto front can get to be pretty big. And also, like, okay, let's say you get a bad sample, right? That just means that now a different point becomes Pareto, right? More likely, it just means you drop that from the Pareto set if it's overestimated. You're not going to have something with exactly the same cost. So if it's overestimated, you're just going to end up dropping something from the Pareto set. This seems important. This is trying to robustify something that might not be able to be robustified, though. Sometimes the M's are just very noisy. I guess that's why Asha would win. Because Asha doesn't care about this type of stuff. All it cares about is the final model, basically. It's not building it, it's not trying to predict any of this. So I'm definitely going to do that as a baseline. Pareto front minimum. We start the Pareto front because the cost itself is a noisy print. That's not true. This is true for a different reason. This is just because you have to train the models for a bit to start getting a curve. 20% observations with the lowest cost. Interesting. Tuning parameters like model size can be difficult if some parameters lead to failure. Okay, so they have a failure prediction model, which you should be able to just know what's going to out of memory and not run that. So we don't care about this too much. Cost ceiling, this is fine. Parallelism. Yeah. Well, let's see. This still might do better than Asha. I don't want to give up on this. This still seems in my mind like this has potential. There's some things I don't like about it, but this still has a ton of potential. Let me just go turn the AC on real quick and we'll get to this. But so let me figure out how this works because I need to understand this sampling. So they take this X, X is sampled around a Pareto value. I actually might like this hard trust region idea better. An issue, okay. We're more interested in the best performing parameters. I don't really understand this. Because you sampled this X from any Pareto point. Uniformly weights improvements across the entire Pareto front. Okay, I gotta look at the code for this because the math does not make sense. See, to me, it looks like you should be biasing your X samples towards higher cost stuff. What this looks like to me is that they are biasing their scoring function. I don't understand. Unless, are they sampling from this? Maybe they're sampling from this. Hold on. So wait, if they... Okay, hold on. I think that they are sampling from this. So this is a scoring function. This scoring function works over everything. We got rid of p-search. We're getting rid of this. So all we have is this expectation here. I actually like the idea of the hard trust region. I'm going to try that. But this thing, this is going to give you a distribution. Instead, what they say is they're going to sample a cost, and then they use this function to estimate the performance at that cost. And then you're going to take a max between these two. But then they take a max over... I think they just take a max over this thing. Max over all candidates. Okay, so how does this work? Let me just oh wait, maybe I do get it. I think I actually do get it. So this is the expected performance. So if you, per point, random for using, there's a chance that it will higher or of the point, lower cost per each point, higher chance that random sample. So for the positive form that random, this means bias points or lower points, which patient higher. This does not seem we really like the full sweep cost budget. So I mean, this could just be parroting back what I said. There definitely seem to be some major limitations with this algorithm now that I'm looking at it. Quite some limitations. There are quite some substantial limitations here, though, for sure. Okay, so I understand how they're doing this. Let me make sure it's implemented correctly. So they take acquisition function. We don't need this. We can just get rid of probabilities. I don't actually see this max cost masking. Always max. This should be, okay, this is the clamp. Let's make sure this is on. This should be on, right? What? It's using the same sample repeatedly here. We'll fix that. Okay, good. This is... They do have this clamp thing. Get rid of this. Okay. I'd like to figure out why all the random samples are the same to start. We'll have to look at that. Let's see if I can find that in the meantime while this runs. Get random. Sample search space 32. Oh, you know what? I bet it's just that we're using the time in seconds. Holy. It's already got 200s? Well, that's a ridiculously fast improvement. It's pretty noisy, but I guess that makes sense. Yeah, it's crazy fast improvement. And we're not even getting good random samples yet. Let's fix that. Yeah, I think the science side effort of PufferLib for the next little bit is going to be hyperprim. That's the biggest bang for our buck. It's so important and nobody does it. I mean, really, there's not any higher return on investment. I'm going to be curious to see whether carbs is the algorithm that we end up using. It's a very complicated algorithm. It makes sense in principle, but there are some rough edges. And like with something that's complicated, there are just so many places to have stuff go wrong. Okay, but this is like dramatically better here. Like we're getting these 200s and stuff. We'll see how long it takes to max out. But we're getting these samples way, way, way faster than before. This used to take like 200 or at least 100 experiments to get one of these. And now we're getting it quicker. There we go, 250. Okay, so this is like twice as good as before by deleting their stupid sampling, like their stupid probability weighting. As expected, that was just dumb. I don't know why they had that. We'll see whether hard trust or soft trust region is better. Hard trust is more conservative. And it should still be biasing to the top end of the range here. Doesn't mean it's going to exclusively produce results there, but it should be producing. Well, actually, it should actually go to the top end because the cost is uniform. So the Pareto points are at the top end. So this is kind of noisy, to be fair. This is kind of noisy. I mean, it might just need more samples to build up the predictive model. It is getting better over time. There's a 67 in there. Still way better than before. Okay, so next thing is going to be this time into time.time. Random.seed. Just take an int. It has to be converted to an integer. Okay, so what we want is I just multiply by 1,000. Well, this is good, right? If I do int. Yeah. That's good. And let's see. Oh yeah. So much better than before. Still gets a few bad samples, but overall so much better than before. Let's see if this fixes the random problem. Seed must be. Okay. What's a good way to get this seed? Way to get Ah, perfect. Lower 32 bits. Seed equals. That's good. Perfect. Now you see we get different seeds. That should actually help the algorithm out quite a bit because the initial data points are properly separated. So that's fixed. Now, let me think about this from here. This is kind of the simplest possible case for carbs because there should only be one Pareto point. I should double check that there is only one Pareto point. It's pretty decent. Okay, so we'll just do like this. So here, oh, they were just multiple Pareto points that had the same output. That's fine. Yeah, that can happen with that could happen. That's fine. Yeah, they had the exact same output and then slightly different parameters. That's totally fine. You say, are this the exact same point? Yeah, these should have gotten merged. But I guess it's a resample. That's fine. And now, why are these two not? Oh, I guess it doesn't distinguish between duplicated suggestions. But this is like never going to happen in practice, so this is fine. This is only because I have a perfectly deterministic synthetic test. So it is sampling around, it's sampling around a Pareto point. It's weird that some of these suggestions are so bad, you know, because it should be scoring this. I guess the Gaussian process takes more samples to be able to build a good predictive model. I mean, this is a massive improvement. I kind of want to now compare this to asynchronous halving. To see how that does. I mean, hold on, that's random search. I also haven't added the scale parameter in yet. So this is making way too aggressive updates is why. So this is like almost random the way it's searching. All right, so let's try that. Try this. Okay, so this is now at 205 here with this many parameters. This is what we have here. Oh. And they're like a cumulative mean or something, and we can just have this. Let's try this. So what this should do is massively reduce the per suggestion search radius. Let's see if this gives us more consistency. Not so good so far. possibly set it too low. So it is making nice progress. It's like pretty darn consistent now. Is it going to be stuck at this rate of improvement, though? Yeah, the deviations are just very small here. It should have a good predictive model, so it should be improving more consistently than this. Oh, you know what it is? Carbs literally is only building the model based off of the one Pareto point. Okay. So that's not amazing. There's a 56, okay. Yeah, so I'll let this run for a bit just to see what the shape of this curve is. I do think whatever I just did is too conservative. Because it basically got one lucky update, and now it's still stuck in this little region. I mean, there are a couple different Pareto points it looks at, I guess. And there it gets an update. It's still just so slow. Okay. Let's try 0.5 on this. 74. So it's doing stuff. It's too slow. So the point of this is the search range that you'd use for like random search or whatever. That's like the goal of that is to cover most of the space. You're trying to do something that's like somewhat tight around the Pareto values, but not so tight that you are basically sampling the same point. We'll see how this does. I mean, come to think of it, I wouldn't be surprised if the really noisy version actually works, because it's basically, if you think about it, if you have a really high mean on this, then it's just random search. Or it's like basically random search, but with the mean variables, the means of everything set to the best run, and then doing that on all the Pareto values. That's actually kind of good. But it will produce like noisy. I mean, the downside is it will produce noisy results. How do they use the Pareto fit? Hold on. Because this model's crap. Whatever this Pareto model is here is crap. So anything that comes out of this model is going to be bad. Let me see. Final model is used as a baseline for the expected. Okay, so this baseline is going to be crap for this because the cost is all the same. I don't know why they only use the Pareto points to fit that model. I guess it makes sense. I don't know. I don't know if that should be a Gaussian process. Okay, so this is better. This is giving you up to 70s to 115. We'll tune this on the full problem because right now we're not tuning on the full problem. So let's go PufferLib. Test curves. So those are the optimals. The full problem should be, there should be cost assigned. This doesn't change the optimum, but it should change how carbs runs. And then we can test this stuff, yeah. This is looking like a decent trade-off. It takes a little longer, but these are like very stable updates. Yeah, so now the acquisition function has been learned. It's just gonna solve. That's pretty decent. The predictive model is not. I'd expect more out of that model though. Because they're supposed to have, this Gaussian process is supposed to be predicting which of these parameters is going to do well. And it should be something that's very easy to learn, but it's just not doing it. Like this should basically consistently be going up, and it's not. Maybe we'll tune it a little more, we'll see. I want to get to asynchronous halving soon because I just don't have a good baseline for this, and I'd like to build out a test suite because if I'm going to spend a whole bunch of time packaging up carbs nicely, I want to know that it's actually outperforming strong baselines, or at least like relatively strong simple algorithms. Okay, so here's cost. We see that it solves. This takes, what is this? Here, yeah, 234. I think we'll count that as mostly solved. Okay, 79 update for this. Call it like 85 to get the 250-ish. So that's way, oh yeah, here, there we go. So $83 updates compared to our synthetic test. Oh, it's about the same. About 83 either way. I have a carb sweep question. When I try to bound, I need to make the background on this less transparent. When I try to bound, hold on. When I try to bound gamma, what branch are you on? Are you on my ablations branch? Oh no, you're on 2O. Huh. Yeah, I don't know, man. That's weird. Um, there are some serious problems with the base carbs, I will say. There's some very serious problems with it. We've made it like it's about 3 times better already than it was before, and I'm not done yet. You can try that. It's going to be jank. So if you're going to do that, that might be jank. You can probably actually, for your problem, it'll be fine. If you just do from 0.9 to 0.99 linear, it'll work. Because yours isn't going to be super high anyways. Okay, so this works at least as well as before, if not a little bit better. This looks nice. Now we got to do the full problem. Now there's cost involved here. When I finish it, man, this is very difficult because I'm wading through a whole bunch of math and carbs, and I'm starting to see some questionable choices that they've made. And then looking at their baselines, it seems like it's possible that I'm going to be able to implement something much simpler that might outperform it anyways. So I really have to do some proper tests on this. Why is cost 1.0? Oh, because I forgot to uncomment this line. Okay, good. So now we have dramatically varying costs and a bigger Pareto front. Was this one with cost or without cost? Cost, uptime. Okay, so this is the one without cost. So let's see how carbs does with cost. It's going to do a little bit differently. I kind of want this one to be on Neptune, though. Really? So we're going to put this onto Neptune as our baseline. There are still improvements that can be made here. But I'm going to do, I think we're going to implement Asha after this as a baseline, and we're also going to do the random as a baseline. So let's just run this here. Dude, what the? I just installed Neptune. Fuck off. Pip is screwed up. API token. Okay. Is there no carb suggest? Where's suggest? Oh yeah, there it is. Okay, let's see how our run is going. There we go. Much nicer. Batch size going up, mini batches, interesting stuff. There may still be some search parameters to tune. Has native carbs integration with Wannabe improved? Nope, they haven't done jack shit. Or have you just switched to Neptune? It's not really, Neptune doesn't do hyperparameter tuning at all. So we're doing our own hyperparameter tuning and managing it via tags. So we'll support Wannabe and Neptune, but we're doing it through tags instead of through their sweeps API. Currently what I'm doing is I found some major limitations of carbs, so I'm making like neocarbs, new version of carbs, and I'm also going to benchmark it against some other baseline algorithms to see if if even my better version of carbs holds up. Because it's possible that we're just going to have a simpler thing that works better. We will see. That said, I have made carbs like 3x better than the original already. So, yeah. This is a synthetic benchmark. Let me see if I have the original result here from before I messed with it. Synthetic carbs. Maybe this one. Yeah, okay, so this is before I messed with it. This is what carbs got us, like 70 or whatever. Exact same benchmark. Okay, and then I did some rescaling work, and I got us to here, 250. But this is without cost awareness. So now, with cost awareness, we will see how well we do. Cost awareness should hurt it a little bit, but what cost awareness does is it prevents you from running really long experiments too early. So the way to evaluate it is you need to take into account the cost of all of the experiments. I can probably do these at the same time. If you set search center out of bounds, carbs yells at you. Yes, that does happen. We're gonna see. So basically, Spencer, if carbs ends up being the God algorithm after these tweaks, then I will invest the time that it takes to really clean up the code. And like it'll be like half the code or whatever. It'll be a file in PufferLib. There are a couple of tricky things like, yeah, you have to load in Gaussian processes and stuff, so it'll depend on Torch, but it'll be much, much simpler. If we beat carbs with something simpler, then obviously we're just going to use the simpler thing. So we'll see. I remember trying to do carbs with Wanby sweeps. Well, that's actually, we do have Wanby sweeps working with carbs in Puffer 2.0 right now. You can do it. It's just that like there are some limitations of carbs that could be improved. I don't know. I'll be somewhat disappointed if this is just beaten by something way simpler. But here's the thing. I'm looking at the paper, and yeah, this is their version of carbs with like a whole bunch of things screwy. But so we're gonna have a way stronger thing than their version of carbs. But like look at Asha. It doesn't do so well on language model and image classification, but for whatever reason on RL, it does the best, and Asha's really simple to implement. Also, Asha has the advantage of being trivially multi-node. Like, we wouldn't even have to do any fancy stuff, and Asha would just be multi-node. It's really weird how different the performance is of these algorithms on different tasks. Like, I kind of don't believe that the ranking isn't similar across tasks. I almost want to think that they were just configured better in some cases than others. Okay, so after 40, we're at 140. We're starting to run the really long runs. It's missed a couple parameters, so I think that there are some configuration improvements to make here, because like it should definitely figure out mini batches 8 and stuff like that. But I think it's also possible just being conservative because this is cost now. Update epochs to 4, yeah. The MEMS, I don't think this matters. Maybe it does. PPT, this is 16K, so we got that. And then for environment uptime, so this should be or cost. Okay, so this is doing the correct thing. Look, it's getting more cost over time. It started out low cost. So this is the correct thing, roughly. I can probably do 2 of these sweeps at the same time. Like, I don't think Neptune will yell at me. I'm going to just do this. And we're going to get a random sweep working. Okay, so now we got to do our setup here. I know it's done well in Puffer because I copied from my own repo with some jack-based M's. It was done, at least originally, it was very finicky. Yeah, it was. Very much. Give Puffer M's a try. They're faster than most jack-based M's, and you don't have to suffer. Though we are starting a collab with Flare to provide nice puffer bindings for CraftX and Kinetics pretty soon. As soon as I get to that. Those ones are pretty nice. Oh, we got a fair few folks on YouTube at the moment. Welcome. So what we are currently doing, we're currently looking at the carbs hyperparameter tuning algorithm, which is, at least on paper, a very good hyperparameter tuning algorithm from ImbueAI. I found some pretty substantial limitations and quirks in the implementation that I fixed. So now it's at least like 2 or 3 times better than before. And now what I'm going to do is I'm going to benchmark this on some synthetic, on a synthetic hyperparameter optimization task I made versus random search, and then probably versus Asha once I implement that. And we're going to see whether carbs is truly the king of hyperparam optimization once you clean it up. And if so, I will package it up nicely, simplify the implementation, and put carbs into Puffer. Or if one of the other baselines is easier and performs just as well or better. And if so, that's great news because Asha is way simpler to implement, way simpler to understand, and would also parallelize trivially to multi-node. CraftX is going to be the focus of one, so it would be very appealing. Yeah, CraftX is a great env. Original Crafter is a god-awful env. It's the worst Python code I've ever seen. I don't even know how you make an environment that slow. CraftX is awesome. That said, I had talked with the authors of these Jacksense and Flare, and they're very talented for being able to do this stuff at Jax. But they're kind of shooting themselves in the foot a little bit. It would literally be so much easier to just implement these things in C. Like, it would be so much easier. It would be the same amount or less code, and you wouldn't have to think in arrays. I mean, we literally have brand new people to RL implementing all the various puffer M's in C, and it's like so easy by comparison. I don't know. If anybody wants to go port CraftX to C, you're welcome to. I wasn't going to do it because like the jack sample already exists and it's already fast. But I would not be surprised if it's just faster and less code in C. Possibly except for rendering. I don't have an amazing way of doing rendering yet, but I mean, their rendered version is not that fast anyways. Okay, let's take a quick look at this now. So all I got to do is update our random sampling code for the new param spaces. If I add a new reward to tune, and I keep the previous bounds that led to better results, or do I have to set everything back? You're probably decently safe, Spencer. It depends how tight the bounds are. So what you would do is you would run the sweep with the tight bounds, and then if when you go look at the graphs, you know the best results are pushed up to one edge of the range on one of the parameters, then you loosen that bound, right? You do a little sensitivity analysis. That's why good graphs are important. And for YouTube folks, discord.gg/puffer. Stop by, come build some RL environments with us. It's fun. And start the repo as well, that helps me a lot. Okay, so here we got min, max. I'm trying to think how I want to do this. There's also like a mean and a clip. Or did I get rid of clip? I think I got mean and scale. Let's just do for now, let's keep these min and maxes. Let's try this, and then log norm uniform pow2. Oh, actually, do we even need this? No, we don't need this because it's a uniform, and then we'll do log norm will be and do that. And with JAX, it can be run on GPU though. Are you saying just writing in C and running on CPU would be better? Yep. GPUs are not designed to process arbitrary logic, and they're definitely not designed to process, like, writing entire games in terms of array logic is kind of an insane thing to do. Like, it's not, CPUs are not slow. Python is slow. All of our environments in C run 1,000,000 steps a second, and we have some of the most complex environments out there. Like here. This thing runs, I think, 1.9 million steps per second on a single CPU core. The simulation of this does. And we train this at like 500K as well. And like this is, here. This is a massive environment with like, you know, tons of stuff going on. There's an economy system, like there's trade, there's like enemies, there's all sorts of stuff going on here. And this is just fast. And all of our environments are fast. Like the faster ones are 10 million. We stopped trying after 1,000,000 because it's fast enough, but some of them are just even faster. Yeah. There are like a few places where there are like things that are hard to make fast, but for the most part, yeah. I don't know what you're on about, Jason. We're not doing like train time rendering for the most part. The rendering is inference time in RayLib. Believe that just running the MO CPU is the total training time. Yeah, there's potentially transfer overhead. So we do some bandwidth optimization. I mean, we have M's training at 1,000,000 steps per second. Does anybody else? Maybe there are a couple like JAX things on really simple environments that do, but for the most part, not really. And like, you're not implementing neural MMO3 in JAX. You're just not. Okay, maybe if you're a total genius, you can write like 10,000 lines of JAX for neural MMO3 in like a year, but it's just, or you can be completely brain dead and write it in C and have it run 1.9 million steps per second, and it's just fine. We train at 500K on that on one GPU. Like, our default training setup is at least 100 times faster than the majority of what is being done in RL right now. Like, every time I get sent an academic repository, it's like 1 to 10,000 steps per second. And then most of our baselines, it's like 400,000 to a million or 1.2 million steps per second. It's kind of nutty. This is how we get stuff done, though. Okay, so this min, max, this is fine. Uniform POW2 is also fine. And then the logs are going to be a little different. It's min, max, mean, scale. What's neural MMO SPS? Last I checked, about 1.9 million steps per second per CPU core. And then the training at the moment with the policy that I'm using is around 500,000 on a 4090. So that's like arguably one of the most complicated environments out there that's still ludicrously fast. That's the nice thing with C, is like I can just make everything fast. With JAX, like when you get to complicated branching logic, stuff's really hard to keep fast or like really hard to represent. It's trivial in C. You just write the code in the most brain dead way possible and it's fast. Whoa, 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 whoa. C compiler, yeah. I mean, but here, like the crazy thing about this is, I'm pretty sure the neural MMO3 code is shorter than the crafter code. And that's like including all the really nice fancy rendering that we did. Like you literally just go here, PufferLib, Ocean, all the environments, and then like neural MMO3 is 1.h file, 2,800 lines. And like if you scroll through it, the code is brain dead. Like this is about as complicated as it gets. It's like conditionals and loops. Like a first year CS student can read most of this. There may be a couple things I do for perf in here, but like a first year CS student from their first systems course can read this because there's nothing fancy at all. I don't think a first year CS student could write this as cleanly. I would hope. I'd hope I do a little better than that. But read it, yeah. Not true of the JAX code. I'm gonna gamma and lambda. Gamma and lambda not getting sampled. Oh, I should switch my view back to this. Oop. Here we go. Let's see this. So gamma. How's this happen? .005, right? Oh, hold on. How do I do this? I think it's gotta be like this, because it's getting clipped. What's happening? I think it's 1 minus max. Man, like this. Still no? That's weird. Getting clipped. It's weird. Scale is 0.5. In .005. I get from .05 to .02. Get .007. Wait, how the heck does the mean go from... I don't understand this, wait. Mean? min, max. Oh, something screwy here. Is this parameter well defined? How is this the mean? Okay, so its max is 0.995. Min is mean should be 0.98. Maybe these are the wrong order. Hold on. Min, max, mean, scale, right? We do switch max and min, yeah, and then mean and scale. Okay, so something's screwy here. Hold on. Mean. What is max 0.98? Min, max, mean, scale. Logit normal, min, max, mean, and scale, right? Min, max, mean, scale. Min. Oh, stupid. Okay. I probably don't need to reverse these now either, do I? Let's see. Okay, that's better. Yeah, there we go. Boom, diada. Gamma, lambda. Gamma, lambda. These are good. PT horizon, yep. Everything looks good there. I think the big one is it's just not going to explore the high end of the total time steps. We will see though. I know nothing about AI. Is there a tool that allows regular players to share their game matches with AI, which is intended to help them learn? Is that outreach currently and probably won't be seen in the near future? It just makes sense for it to exist. Thanks. I think people have done kind of shitty versions of this for individual games. There's not just like a plug into any game and have it work. To help AIs learn, oh, that's separate. It's still going to be per game. There's not just a thing that's going to take arbitrary data and solve it. We're still at the point where like you need to have, there's a fair bit of per problem work to be done. I mean, the closest thing that I've seen to what you're describing, there's this really funny League of Legends tool that you can get where you can get like it's like an AI that looks at your screen. It's probably a GPT wrapper or something. But then based on what's going on, you get Tyler One yelling at you for being stupid, which is pretty funny. So it's like this like fake AI coach thing. That's the closest thing I've seen. I don't know if this is useful, but it's pretty funny. That's not bad. So just random search, I mean, doesn't solve the task. The cost is too low. I mean, it's not going to explore the full range unless you set it. Hang on. Where's my window? Okay, this is almost done. So we can compare to neocarbs. Okay. It doesn't quite solve the task either here, but this is with the cost awareness. It's not doing higher cost over time. So something seems to have gone horribly wrong here. I'm surprised it's found... I'm actually kind of surprised that it's found solutions this good at this low cost. What did it do? Any batches? Got lambda spot on, gamma spot on, update epochs. BPT horizon's off a little bit, but I guess it increases cost, and numems is spot on. So I guess it did everything perfectly except that it didn't want to increase the cost via time step. So it's a little too conservative here. So that's why it's not full solved. Interesting enough. Now, if I just do, I'm pretty sure that if I just do, if I just set this to 1 real quick. Oh, it's a little better, but it doesn't full solve still. It does explore the higher cost ones, but it doesn't full solve still. Okay. I mean, it's random search. You don't expect it to really do too much. So the next thing is going to be Asha. I really wish that there were random search as a base, if like random search would just be a baseline here. Let me just make sure before I invest time in this that I think this is going to be reasonable. I think I got a little jumbled among my own words. I saw some of your games on Puffer. What if the game was played by real people? Would it be possible to improve these bots? Yeah, so yes, that is possible if we set it up to collect data. But the thing is, you need quite a bit of data. To give you an idea here, these things, like these games that we have, when we train these, they are so fast. Like you see this running in real time. But when we run this for training, like this game runs at hours of gameplay every second. It runs at like 10,000 times real time or something ridiculous like that. They're just very, very highly optimized. So like this one, for instance, we literally trained a model to play 2,000 years worth of this game in a few days on one GPU. So the amount of human data you need is quite substantial in order to get like really good stuff out of it. It's also just not the area that I work in. For the most part, like most of my work isn't on human data, it's on like learning from interaction. So I just haven't really gone too far down that route. The methods in that area are generally pretty easy and better established, whereas the area I'm working in here is like a way less developed area of science. There's just like a lot of potential for improvement. But yeah, this environment here, if each like time you see it move a tile, that's one step. This thing runs at 1.9 million steps per second on one CPU core without rendering when we run it for training. So yeah, these things are just like unfathomably fast. They're all implemented in they're all implemented in optimized C or relatively optimized C. So they're fast. Okay, so here's our random baseline. You know, we average it a few times. It's probably like 180, 190, something like that. Let's go look at Asha. Back to review mode. So carbs is a very complicated method. It's quite possible. What was this in? This is not it. Carbs in view AI. Let's do this. So carbs. The reason that I'm a little suspicious, right, is they do all of this math. But they don't like smash the baselines, right? It seems like they're really just the first ones to throw this on RL. And they lose to Asha by quite a lot. But the thing is, Asha does worse on... Well, actually, no, it wins at language modeling. It only does worse on image classification. It almost seems like a bug, because I have no idea why it would just, like, randomly be way worse at that. Let me see. Because, like, okay, TPE and HEBO are pretty consistent, right? TPE is consistently a little bit ahead. Then carbs is... Well, it's not ahead here. Okay, so there are a few shakeups, I guess. So this result bothers me that Asha's way down here. Carbs performance is consistent across tasks. I mean, not really. It sucks at language modeling. Oh wait, lower's better here. Why would they do this? What is wrong with them? What the hell's wrong with them that they do episode reward accuracy and then cross entropy? Okay, hold on. So, okay, Asha is like second to carbs here. It's the best on RL. And it's like the worst on image classification. Much lower variance distribution of outputs. That looks pretty high variance to me. They have more variance on RL than Asha does. I have no idea why it would be specifically better for RL, but let's see. Let's go read this thing in a little more detail. It's 2020. I wonder if there are better algorithms since then. Let's see, Optuna. What hyperparameter algorithms do they have? State-of-the-art algorithms. Not clickable. Where are your algorithms? Grid search. Okay, here's TPE, which we saw. Right here's TPE. It does not so great on language modeling, not so great on RL, and pretty well on image classification. They got CMAES, GP is just kind of generic. Non-dominated sorting genetic algorithm 2 in quasi Monte Carlo. This seems to not be okay, so it seems like really there aren't like updated libraries with all the good algorithms. This seems very neglected, a very neglected area of science. Let's look at Asha. Scales linearly with number of workers, yep. They offer this as a service. This is like 100 lines of code that they offer as a service. That's funny. Where's this from? CMU, Google Research, and Determined Data. Okay, so some startup. Okay, so this is what they use. Sequential methods. We don't care about this. Asha algorithm. Successive halving. The need to adopt it to a okay, this is silly because it's trivially, this is embarrassingly parallel. Allocate a small budget to each configuration. Evaluate all configurations. Keep the top fraction. Increase the budget and repeat until maximum budget is reached. The resource is going to be wall clock time, obviously. Input. Number of configurations n. Minimum resource R, maximum resource R. Reduction factor n. Minimum early stopping rate S. Okay. S max is log. Okay. T is get hyperparameter configuration of n. So you get n hyperparameter configurations. So you get, what the hell is this? Ni, Ri. Okay, I don't understand what they're doing with this, but this seems like a very simple algorithm. You're basically just getting the top K. It doesn't seem like they're adding more configurations back in. Takes more resources to explore same number of configuration. Okay. So this is literally just like run some configurations, keep the best ones, double the time allocated. Very simple idea, unless I'm missing something. I'll drop this into Claude in a second. I use it just to sanity check I'm not missing stupid shit. Straightforward ways are not suited for parallel regime. Embarrassingly parallel approach. This is not suited. We would like results in little more than the time to train one config. What? I don't understand. Assume training time for a configuration scales linearly with allocated resource. For a given bracket, the minimum time to return a configuration trained the time needed to return a fully constrained is just 3 times time, since there are 3 rungs. Each rung is allocated to R resource. And return an answer in just R time. I don't understand that at all. So let me see. Maximum resource R. Evaluate all configurations. Increase budget until maximum per configuration budget of R is reached. Oh, I think that they're trying to like reduce the number of configurations by at least a factor of 2 and then double the resources allocated. So they're running half the number of jobs for twice the time or something like that. This seems very arbitrary. And they say, within a bracket, each round of promotions are rung. Okay, sure, whatever. Another naive way of parallelizing should distribute the training of the n over n to the k surviving configurations on each rung and add brackets when there are no jobs available in existing brackets. Synchronous SHA. SHA's synchronous nature is sensitive to stragglers and drop jobs, as every configuration must complete before proceeding to the next rung. Estimate of the top one over n configurations for early stopping does not improve as more brackets are run, since promotions are performed independently for each bracket. Okay, let's see what they're doing. I think they're vastly overcomplicating this. This seems like a very simple algorithm that they're overcomplicating, unless they're doing something very, very clever right here. I mean, the idea here is literally just like randomly sample parameters, run them all for a short amount of time, see which ones do well, keep those, run them for longer, repeat. That's it. We now introduce a SHA, effective technique to parallelize SHA. Promotes configurations to the next rung whenever possible, instead of waiting for a rung to complete before proceeding to the next rung. If no promotions are possible, Asha simply adds a configuration to the base rung. The more configurations can be promoted to upper rungs. Its asynchronous nature does not require the use of a pre-specified number of configurations to evaluate, but it otherwise requires the same inputs as SHA. Run then return value loss is asynchronous, and the code execution continues after the job is passed to the worker. Promotion scheme is laid out in the get job subroutine. Okay, so whatever. They're doing things. Whatever. The only place we would possibly do this, we're probably just going to have one job of these per node, unless we're using a really tiny networks, in which case we could just run this on CPU and see what happens. I don't think it's much faster though. Our fastest training configurations are about 1 million, 1.2, and then usually we get like 200K or something on CPU. So unless I'm wrong and unless the CPU is way faster, like 16 times 2, well, 200, that's still 3 million. Maybe it's worth CPU, we'll see. I mean, technically we could do both. We could have GPU and CPU drops. That'd be kind of cool. Asha is well suited for the large-scale regime. Wall clock time is constrained to a small multiple of the time needed to train a single model. I mean, that's kind of like PBT. Population-based training. Population-based training is a pain in the ass to parallelize, though, if you really want to do it well. I mean, there's a naive method that's kind of decent. Yeah, no, population-based training is really, yeah, that's not really easy to parallelize. I think we're going to stay away from that. Also, this is not a concern for us. We're not small multiple of time to train a single. This is what you do when you have like hundreds of nodes. (13/9) times time of R. 9 machines are sufficient to promote configurations to the next rung and the time it takes to train a single configuration in the rung. Hence, training time for a configuration in rung 0 is 1/9 of the time. One rung, it's 1/3. For rung 2, it's time of R. Log n machines are needed to advance a configuration in the next rung the same time it takes to train a single configuration in the rung. Okay, I don't really understand what they're doing. We're going to look at the pseudocode. Hyperband simply runs multiple SHA brackets. We can asynchronously parallelize hyperband. Interesting. So let's take a look at this. For each worker, get job, run then return val loss. Completed job, update configuration theta in rung k with loss L. So what do? They do for k is log I think they're just running fewer jobs per machine is all. Oh, do they have a comparison to PBT here? No, PBT is pen tree bank in this case, okay. Let's do what is Sherpa? Oh, okay, hyperparameter algorithm. Oh, cool. They have they got PBT. They got async. Really cool. Very nice. We'll see how their implementation looks. Did what? Why? Where's Asha? Algorithms. Sherpa algorithm success of halving. There's algorithms. My guy. Where? Where is this? It's the wrong freaking. Is this the wrong one? Oh yeah, wait, this is the wrong one. Isn't it? Wait, didn't I click this from here? Okay, there we go. Me dumb. Sherpa algorithms. Okay, good. It's simple. There we go. Oh, what a nice library. This is nice and simple. Good job. Yeah, this is good. They have course, they have spaces, study. Search. Grid search. They actually have some nice little algorithms. I could just try all these on our synthetic test as a baseline. The only thing is I don't know if they've handled the space transformations correctly. Though I can probably benchmark their version to start and then see if I can do better. That might be a fun thing to do. Yeah, let's do that. Because this looks really simple. I'm not going to add this as a dependency to Puffer, it's just not happening. But we will use it for some tests, see if we can beat carbs. Just, out the gate. I think this will have finished by now, yeah. So here's neocarbs. Not bad. I got to about there with the full thing. This is with cost awareness. A couple little quirks here. I think we could make this still a fair bit better. But let's just see if we like instantly crush this or anything, right? Okay, you do not need Keras. Good. And they do have log. They don't let you specify mean. They just let you specify bounds. Oh, it's not terrible though. Like this. What the hell? Dashboard? I don't know. I'm kind of tempted to just do my own implementation of this. They've got a bunch of obnoxious stuff here. Some dashboard, their own spaces. Yeah, I think we're gonna just do our own. It's only like 100 lines. I'd rather do that than have to implement this, like to add bindings for this stupid thing. Just popping in as a comment. Going well. Running new tight sweep. Use your logX trick. Should feel like make the sweep like 5 billion steps. Writing 3D comp. Graphs just go up and right. Yeah, I mean, they're gonna go up and right on log scale, maybe. But, like, should it take 5 billion steps to solve a simple level of your puzzle? Probably not. Let me do this back to here. Grab this. I mean, it starts with random, right? Promoted trials. Oops. 3, 1. Okay, so it's just get suggestion, I assume, as their API, and then it just calls everything. So we do job. You start this with okay, I see. So I don't know why they have a data frame. Jeez. This is like very short but very confusing the way it's implemented. I really don't like the way this is implemented. So let me see. You get a job. Get job is check if there is a promotable config. Minimum resource that each config will be trained for. Maximum resource. Elimination rate. Minimum early stopping rate. Okay, that's not bad. Yeah, that's not bad. You get a suggestion. Job. Top end. I don't see how this is working. Seems like you need to run a bunch of trials before you do this. There's something tricky here because if you initialize this with 16, how many times do you want to double this thing? Like, probably have 2 different cutoffs. Mm. And I think all this is just for a baseline. Okay, hold on. We can do I think we can essentially do the maximum performance of this we can essentially get the maximum performance of this without implementing it. Because the thing is, it's based on a random search. I think that's fair. Let me see something. I think if we're being smart here, we can get the performance of this thing. Okay, so all we have to do is, well, if I just do like args train args sweep. What if I just do this? Is this correct? Try this. Oops. Okay, so here, okay, so this does not consistently solve this benchmark, even at max cost. It gets close on some of them, but it's not consistently solving this benchmark. Let me think if there's anything I'm missing here. There could be some parameter adjustments. I think. But yeah, there could be some parameter adjustments. Hold on. So this uniform is, these are just selected randomly, which is fine. How to. No, I think that these are pretty good. So if we do this, right? Okay, so here we have 263, which is solved. Those are very good hypers. This is 200 experiments, though, and not consistently solving in 200. So basically, the premise here is that ASHA is random search with basically compute adjustments on it. But if you're going to start with 200 experiments, then ASHA is not going to do better than just running those 200 experiments for the full amount of time. So this gives us an upper bound on ASHA's performance. It's going to drop some of those. It's actually going to be a little worse than this. And this is not full solving this task. And I believe that you should be able to solve this task in less than 200 samples. So this is not going to cut it for us. Which makes sense because, again, it's just based on random search. It's not adaptive in any way. So, I mean, it can probably get pretty close to these numbers, which is like decent. But my guess is that the reason that it looked good on the baselines versus carbs is just very under-tuned in the original implementation. So basically, whatever we do is going to have to be adaptive to some extent. I think carbs really does make the most sense. There are just some small algorithmic adjustments and some code quirks that we're going to have to address. So this does give me more confidence investing more into carbs. So I'm going to use the restroom real quick. I'm going to get myself another cup of tea, and then we're going to continue on carbs. So having a stronger baseline, because this is basically upper bound of random search is what we just did. So yeah, be right back. You know, it's occurred to me that we should look at some of the other baselines versus carbs on RL, because OSHA should not beat carbs. Carbs should be an improvement on HEBO, which should, this should very handily beat OSHA. OSHA is a very bad algorithm now that I'm looking at it. So let me see why that's not happening. Too many tabs. Too many tabs. Where'd the paper go? Here? Yeah, so this is a bad algorithm. Back to review mode. Where is it? Okay, reinforcement learning. So OSHA's up here. Okay, carbs is second best. So the fact that OSHA wins here is insane. Terminates lowest performing runs early. It's able to sample many more parameters than other algorithms. That doesn't make sense at all. Because the thing is, whatever the length of time is it's running those early samples for is about the length of time that carbs should be running its early samples. So basically what that means is that the carbs, and OSHA doesn't build a predictive model of performance either. So what should happen is carbs is going to run a bunch of quick experiments like OSHA does. But unlike OSHA, it should be running a predictive model of performance. It should be building a predictive model of performance, which then allows it to more intelligently select better parameters for longer runs. I guess what OSHA does is it just says that, hey, whatever parameters I happen to randomly sample that turn out to be good, just keep running those. But that's not quite what you want to do. You really want to be able to look at the good runs and then search locally around those, because and use a predictive model of performance. Like most of the variables in a hyperparameter search are pretty damn easy to fit. They're like mostly independent and they've got a stable region, or like it just like more is better or less is better, you know, something like that. Does this outperform HEBO on everything? Yes, it does. Okay. HEBO is a simpler baseline that carbs is built off of. It's not hugely better though, but the cost awareness is important because I don't think these tell the full picture. Okay. Things to modify next on carbs. We've got our current performance right here. Okay, so this is cost aware. And then this one so this gets up to about there, and then this one, the non-cost aware one solves in like 80-ish samples, and it actually gets even like a little last bit of perf at the end here. You can see it gets pretty well up there, and then it does the total time steps towards the end. Okay, so maybe, wait a second. Something screwy here. Let me go look at the formula I made. Maybe there's something screwy with the test. Log 2 of total time steps. How do they get score up here? How do they get score up here without the total time steps being up there? Okay, I think there is something potentially screwy here because total time step should have more of an effect. Something is quite screwy here. Let me just make sure. Okay, so 254 is supposed to be the max. It found a 262 somehow. Hold on, what the? Something's bizarro. Oh wait, this is 1E9. This should be. Is it 1E10 is the max? Okay, yeah, 282 is the max. But something's screwy there. Oh, I see. Oops. Let me think how I do this. better. $27 is like too small for most problems. Shouldn't even be sampling there. 5. Square root of batch size. It's not bad. Okay, that's probably better. Cost is going to be million minimum. And this num_m is okay, good. Let me see if this does anything different. No, I kind of don't like. Well, this is fine, just scaling total time steps. I think this is fine. I think what was happening before is that the time steps on the score just wasn't very sensitive. It should be the case that, like, okay, so this is 0. Let's do +1. Okay, so that gives you going from 50 million to a billion. 28. Yeah, so that actually gives you a reasonable score. That's better. Let me see just off of this. Hey, welcome. Let me see just off of this. If there's a substantial difference. And then while this runs, we'll look at other algorithm stuff. Test carbs. Where's this? Test. I don't want to wait for frickin'. We don't need this anymore. Do I want to wait for Neptune for this? I kind of should. So this should... Get my token. And then this is the full task, right? Yeah, the full cost aware task. Good. So let's see if that changes anything. And we'll see which parameters, if any, now are screwy. Oh yeah, they're what are we printing? Score? Cost. No, this isn't good. They're all the same. They're all the same score. Okay, let's figure out what the hell's wrong with this. Oh, duh. So that's like max score. This will actually be a nice test. We should scale this so that the max score is like 100 though. Anything how to do this? Eh. Maybe at the end. Let's just run this. Let's just get this running. Actually, and let's make sure we remove these. Doesn't mess up our run. There we go. So the max is now like 3,000 or whatever. Where am I? Oh, this is not doing it globally. Okay. Let's make sure we get Neptune on. Wait, test carbs. Yeah, right here. Okay, so that'll run. Check a couple quick things. So here's neocarbs. We'll see what this does. In the meantime, we look at the paper again. And we look for things to improve. This doesn't work quite the way I want it to. It's mostly these two pages, math pages. They've got 3 Gaussian processes. It occurs to me that you could get dramatically more training data for these things by giving it every single checkpointed output of the model. I don't know if I want to do that though, because it basically presumes that your graphs are nice and stable. I could just make sure that they are. It's a little tricky though, because if you need to evaluate 10 million steps worth of data for something to be stable, those perf numbers are already old. So I think we'll stick with I guess we stick with the current model. I mean, how many points do you need to train a Gaussian process? Ten times for basic training. GPs scale poorly with data. Use need some full solve puffer merch. Once we get there, you don't start making merch until you've got a bunch of revenue. And we've got only a little revenue at the moment. There will eventually be puffer things. Let's solve RL first. Freaking Gaussian processes, man. All right, well, that's actually looking way better. Look at that, 39 points and total time steps. It's properly increasing. It's a little early. I would like it to have full correct hypers. And they're pretty close. Hold on. Wait a second. This is really close. Okay, it's missed update epochs. That should be 4. It's literally just missing one parameter after only 42 trials. That's very good. Let me look at what we have now. So we've gotten rid of p-search. We actually don't have a trust region at the moment. This could occasionally get us a bad sample. We should compare this to hard trust region. That will be an experiment worth running. Yeah, so we will compare this to hard trust region. They did not run that ablation. That seems like a reasonable thing to do. Yeah, and the normal centered on the mean as well is like, well, hang on. Yeah, no, I think the uniform is probably better. I mean, is normal a better distribution, actually, if you think about it? Because, like, if you run a normal distribution, right, most of your parameters should be closer to the center, and then you end up with, like, a few parameters that are more deviating. I mean, you can solve that just by generating more samples, though. It needs to be clipped either way, I think. Because otherwise you get outside the support of your Gaussian process. So I think that they're correct in doing a trust region, but it should have been a hard trust region. Their soft trust region is too. It has weird interactions with your other parameters, so we're not going to do that. Let's look at the acquisition function clamping. This is the really weird one to me. And they do have an ablation for it. So no clamping is a huge fail here. No Pareto, huge fail. And the no resampling actually is not going to hurt us at all in the current test, but it will hurt us in the real ones. No Pareto presumably is just they do the max. So they turn it from a Pareto-based search to like a, essentially just turns into a simple genetic algorithm. No clamp. And this is what they mean, right? Let me think about this. This kind of does naturally like push up the time allocation. Because as you sample points that are longer, then you push your samples towards that end of the distribution. This still is not great though. This is possibly the weakest part right now. How are we doing here? Over here. Ooh. What the hell happened? Did it just get bored? And start doing other parts of the Pareto front? Where's the Pareto front? Cost. Is there not already a Pareto front in here? I thought I had one. I guess not. X-axis. Okay, so this is the Pareto front. To be fair, it is actually very nicely filling this in. Let's see, 11415. Doesn't seem to be biasing strongly enough though to over here. Yeah, I think it's just trying to sample lower cost regions. You see the cost goes up and now it's like kind of all over. So what would cause that? I guess just this acquisition function, maybe. It's a very inelegant way to do this. They're just sampling on log scale. So like, if you have 10 seconds, 100 seconds, and 1,000 seconds, a third of your runs are going to be the really fast, stupid ones. A third are going to be these like 100-ish mil, and you're not really going to sample that much at the top end, are you? But I mean, the question is how strongly you want to bias. It seems like it ought to be a function of the confidence of your predictions. Doesn't this, wait, doesn't this give you a variance? The Gaussian process? It does, doesn't it? So like when you stick this into GPY, it should give you variance. Let me go find the code for that. I think that's going to be the major thing I can do. This is going to be a bitch to write a blog post about with all this math. I'm going to have to simplify this so much. Okay, so here you get your samples, right? Surrogate model dot observe surrogate. Ah, you see this? It has right here, it has the surrogate variance in it. Okay? And then there's this exploration bias. So we have expected improvement. EI value. Let's see. Acquisition function value. Okay, so this acquisition function value is just the EI value. You've got a thing for success probability, a thing for max cost. This is fine. It's right here. Expected improvement. Carbs utils. Oh, Jesus. Okay, what is this? Well, there's a link. So it's this function right here, or this function right here, and it should be, where's mu minus best mu minus exploration bias. Probability of improvement. Upper tail probability. Obnoxious. It's this probability, how much we can improve. So expected, this is it. Select the point that minimizes the distance to the objective evaluated at the maximum. Maucus proposed. Okay. JB Maucus. Feel like I'm being mocked here. What the hell is this? You've got, let me see what the parameters are actually going into this. So you have the Gaussian process's prediction of mean and variance. Okay, and then you have mu, best mu, which you're using as a baseline, and then some fucking exploration bias. So prior sigma, okay. Z is going to be mu minus best mu minus bias over sigma. Divide by standard deviation, fine. Original form is this, and then simplified form is what the, okay. Original form is sigma times log prob of Z. Didn't we just multiply by sigma? Oh yeah, but it's, okay, it's over, fine. So it's sigma times log prob of Z, 1 plus Z. I have no idea what this is. And then there's even more. Okay, great. Do I have to care what the hell this is? Or is the change I want to make independent of this? How does the variance even come into this? If it's the expected improvement. Let me see if I can get GPT to like freaking, or Claude, breaking my freaking head here. Oh wait, hold on. I know what I want to do. I gotta figure out the math behind it. Expected improvement over baseline is also normally distributed. Okay, so breaking it down, this is standard improvement. So you penalize the uncertainty, you remove the ReLU, and then weight by cost. So the improvement is going to be mu minus sigma minus best mu. Okay. So we make this pessimistic. And then what does this thing propose? This is times cost. 1 plus cost variance over cost. One plus cost variance over cost. I'm trying to think. I don't like this because this isn't an estimate of improvement, right? The idea is to weight heavily. We want to weight heavily towards high cost, but heavily penalize uncertainty of the estimate. How does cost come in here? How does cost come in here? Okay, so this is what they're doing at the moment, which is really fucking stupid. This is just like sampling time in log space, or biasing by a log factor in time. They're just using this as a baseline. Now what we want is we want the actual improvement over the Pareto point, right? This is a deterministic sample at the moment. But that's actually fine. Yeah, because it is the max. Okay. So you generate samples. We make the expected improvement conservative. We subtract the true Pareto baseline. And now how do we bias this? So we're going to get rid of this clamping. Okay. I mean, the cost uncertainty should be pretty darn easy to predict. Do we want to upweight? We want to upweight high cost. Let's do this initially and then we'll see. Let me see what else I want to do with this. So I think I'm just using this thing as like a sanity check, basically, to make sure I'm not doing something like obviously stupid. It will absolutely suggest insane things if you let it. It's not even a consistent sanity check. It's just better than nothing. Semi-intelligent rubber duck. Directly scaling cost, predicted cost performance relationship. We do have that. If instead of scaling by cost, why don't we scale by absolute performance? So performance improvement, you do mu minus sigma, variance, and Pareto mu. Predicted benefit. Okay, so this is the performance of the cost. Let me see this. Okay, so we get relative performance. Then we get absolute performance. Does this work? Is this insane or does this work? Likely better than the current Pareto front from high relative improvement. Likely to achieve good absolute performance. To be weighted sum. Different powers. Let me see. I think we try this. I see. Let me see this. So do I need to make this conservative to start with? These are kind of two separate improvements. But they are somewhat linked. Also. Where's the relu? I don't see the relu. Expected improvement. I don't see the clamp. It's supposed to be nope. There's no max. So I don't see the relu. So clamp. Okay, well, let's just see if this completely breaks everything, right? So here's neocarbs. It does, like, interestingly, conservative. Okay. Just wait until it gets past random at least. I'll go use the restroom and we'll see if we get any points here. Making it conservative. I mean, it seems like it should help. It might not. I think I'm going to keep it as long as it doesn't completely destroy performance. Because it makes sense to do. The idea here is that the Gaussian process, one of the nice things about it, is it gives you the variance of its predictions. So if you just subtract the standard deviation, you get a conservative estimate of performance, which then naturally upweights the confident predictions, which should lead to like smoother and cleaner graphs where it's not just like sampling points that randomly just get terrible performance and wasting an experiment. I don't know if this one change alone is going to be enough to see a major difference. But then what we're going to do is, this is definitely a problem here. Let me see. So this pattern is definitely a problem. It's just spending way too much time on just bad data points. And you can see here, it's running too many short runs. Even at the end here, it's just running too many short runs. It hasn't full solved this. Like, it can get substantially better performance than this. Let me see what it's missing. It's actually pretty funny because the Pareto front, if you look at this, most of the points are on the Pareto front. So it's not doing like bad experiments. It just has too many experiments down here, and it hasn't done enough up here. It should be like having more of them out here because, yeah, it hasn't gotten all the way full solve yet. This down here is especially bad. There's no reason for it to be doing this. Though I guess technically it's still possible for carbs to do this, but only once it's confident that there are no more improvements at the top end. And I think I checked this, and I think that the maximum was like 3,200, 3,500 something. So I think there is more perf. I will double check that, but I think that there is more perf to be gained. Okay, that's nice and clean to start. We'll see if it continues. Let me use the restroom. I'll be right back, and then we'll let this thing run for a bit, and we'll work on the new acquisition function. 1 second. Let's mute this. Forgot to unmute my mic. Oh, you're supposed to tell me. I've been talking this whole time. Whatever. This is good. This is, I mean, the summary is that this looks better than the other one by a little bit. Right up to 1600. Starting to widen a little bit, but this is just from adding conservative bound. So up to 1600 versus on here. Hold on, if I do this, I guess these look kind of similar. I don't think the cost looks similar though. So hold on, if I look at the costs in the same time period, right? It's like here. Cost. Maybe kind of similar. I mean, I said that if this doesn't horribly screw stuff up, we're going to keep it, right? Wait, 2600. What was the highest floor on the other one? What's the number to beat? Oh, we're actually better already. This only gets to like 2500 all the way over here. Yeah, we're all the way up to 20. Okay, this is cool. Whether this is statistically significant, I have no idea. But it looks good. This is a relatively small change, making it conservative. I don't expect this to magically solve everything. Hopefully it doesn't just magically crash everything either. I'm not going to let this run all 200 without doing anything though. So let's go. Okay, so we're going to do a few things here. We're going to do this, first of all, get rid of that. And then acquisition function, it's going to be the conservative expected improvement. And what did we say? We have it in here somewhere. Yeah, so we do relative improvement, we fix this, and we do absolute improvement is going to be mu minus sigma, and then we multiply them. Absolute I equals absolute score equals and let's see if it's utils expected dot square root. Dot square root. Okay, and then what we're going to do is multiply them. So it's going to be times conservative absolute. So this will be the new one. We'll add this here as well. Now this is dramatically different. So this might take some tuning and such. This is a big change. Okay, so this looks to be about the same as before, frankly. Which is fine, it doesn't break stuff. We've already gotten the good runs out of this. See, 91 items, so about halfway through. Oh, actually, this is substantially better. You see, look at all this garbage down here. So this is actually substantially more stable than the other one. So the conservative bound actually does do something. That's nice. I did a math. Cool. Let's kill this. And now we're going to see if this runs. Oops. Ah. MTI. Let's see if this does anything. We're going to have to monitor several different metrics here. Might be too conservative, might be too aggressive. This is a big change to the acquisition function, so we will see. Big change. We still have not tuned scales fully, and a few other things. But I think that this is the biggest spot for improvement here. Let me think if what I've done makes sense. So initially, they had this soft trust region on top of a normal that was unintuitively constraining your search range so that you could not find parameters far enough from your starting point. It was really biasing you towards the samples that were basically identical to the runs that you've already done. We got rid of that. So now we have more aggressive exploration. Before, they were biasing towards higher cost explicitly by adding like a log weighting term to the cost, so, or to the acquisition function. Now instead, we bias the acquisition function by a conservative estimate of your absolute performance, which is the thing we care about, not cost, right? So if cost and absolute performance are correlated, this should be fairly similar, but this should prevent you from doing long runs that don't really do all that well. Let's see. We also made the expected improvement itself conservative. So this accounts for the variance in the model. So the goal of all of this is that we should get much cleaner curves with fewer points way off of the Pareto front. That is the goal of this. Things to change potentially still. We're still using normal sampling. I would like to compare this to uniform sampling, because normal sampling doesn't, it can get you out of the support range. We can also compare normal sampling to, or we can compare that to clipped normal sampling as well. We could just clip. I don't think that there's anything here to think about. I think this is just empirical. Yeah. I think this is correct as well. I think we'll try that next. Oh, wait, 37 samples. Is this comparable to before, or is this better? It's a little better. We'll see if it keeps it up. It is nice to make, well-motivated changes to an algorithm and actually see it do something. It's pretty good. Let's see. So it's got the batch size correct already. It's got many batches correct. I don't know why it does this. It's pushed learning rate way too far down. And I don't know why. Gamma, it's hovered around 99. That's fine. Lambda, it's pushed too high as well. I don't know why it pushes lambda this high. There really shouldn't be any reason for it to do this. I mean, the model must just be learning a false correlation at the start. We'll try the uniform sampling next and see if that changes anything. Okay, update epochs is very nice. BPT horizon is perfect. I'm surprised it hasn't even sampled anything outside of this. NumEms is now correct as well. And it keeps a nice low cost. And here's our Pareto front. This is very nice. Now the question is going to be whether it maintains like a sharp curve, or if it still meanders around too much. the shape of this curve is going to matter a lot. This is cool though, like these are like good, well-motivated changes to carbs. These are very good, well-motivated changes to carbs. We're gonna see what this does when we throw it on a real environment. Cool DM. Ooh. Okay, so this is the 2000. Did this happen before? Actually, yeah, let's just do both the curves. Why not? So this is what it was before. And this is what it is now. That is a steeper, that's a steeper curve with fewer points. Now it hasn't gotten like this big jump yet. But this is very good. Very good indeed. I'm pretty happy with this overall. Yeah, that's great. Man, this is very nice to see. You know, this is like a very intentional, theoretically motivated change to carbs. And at least on this synthetic test, it's doing exactly what I think it should be doing. Now, I mean, we'll see on real environments when there's a whole bunch of noise involved. That's the main difference, I guess, right? The relationships between hyperparameters aren't perfect, and there's a bunch of noise involved. So we'll see if this transfers. But, I mean, they really can't have done that many experiments on the original carbs, because ProcGen is just stupidly slow. So even though they have a bunch of GPUs, like, they're literally training at less than 1% of the speed that we are on most of our environments. You know, so they really can't do very much with that. And then large language model experiments are going to be crazy slow. So like, I don't know, I'd honestly believe that I fiddled with this as much as they have. They didn't mention any synthetic tests either. So I don't even think that they did like the rapid development like this. I think that I mean, this isn't even that rapid to be fair. Carbs is kind of slow, but like still, Yeah, this is solid. Holy. The question is, where is going to be the end behavior? So total time steps increasing here is very good. Batch size, just the right part of the graph here. Batch size is set. Mini batches is set. I don't know what it's doing with this, with the learning rate, where it goes too low. I have an absolute value on this. It really should figure this out. We'll try the different sample bounds and see if that changes anything. So gamma here is pretty good. 9, okay. And lambda, it's starting to figure out lambda, but like, I don't know why it goes up here in the first place. This seems very odd. Like, this is drift. This is like individual hyperparameter drift. But the thing is, these are fully independent. It should be trivial for this to figure out the value of lambda, which should be 0.95. Update epochs is correct, BPT horizon is correct, numems is correct, and then cost is nicely scaling. And then the Pareto, well, this Pareto front is a mess because this has 2 experiments worth of runs on it. Okay, it's starting to level off a little bit. But it needs total time steps in order to max out the score, is the main thing. And with the current version of this, it will not max out current time steps until it's confident. At least it shouldn't. That's actually good though, because if it takes, this curve up here is actually not as good. Like, this is too many experiments that are expensive that aren't really doing very much. We would rather have more experiments early that are quick and then consistently get the high performance later on. So we'll see if that happens. This one looks good. Oh wow, look at that. You see? So it didn't up the cost, and it's still finding better parameters at the current cost. So this is good because now we're no longer, the previous version was biasing towards high cost. They literally had a bias term to do this. But now we have a bias term towards better performance, not higher cost. And you only get higher cost when that's the best way to improve. So this is this is the cleanest hyperparam sweep I've ever seen so far. I'm sure that it's gonna pitter out a little bit at some point, but we're gonna see if it gets closer to task solve. Main problem at the moment is the drift. I do not understand this drift. Well, lambda's fixed here. Total performance. Predicted performance landscape. It's kind of hard to check. I'm going to try the different sampling thing before I do this because it could technically be from the normal distribution. The normal distribution will tend to keep parameters pretty close. Maybe there's not enough data diversity in the sampling. I don't know. This is very consistent. Holy hell. This is very consistent. Holy hell. Look at this. Only thing you could possibly ask for here is that it's quicker. 109 trials for this. But look at the total time steps. Holy, look at this. It's actually it's getting this perf with this low time step. So I'm curious to see the end behavior of this. Let me see. Okay, so I think it's pushing the learning rate back up slowly. Gamma is now correct. Lambda has corrected. Update epochs is perfect. This is perfect. This is perfect. So what does it have left to fix? I think just learning rate is off now. It does. Is it going back up? I don't have this wrong, right? Let's look at cost over time. Look at that. I mean, this is so much better. I'm just gonna, while this finishes, I'm gonna answer a DM over on the side. Cool DM. It's very nice. This is the cleanest freaking hyperparameter sweep I've ever seen. This is pretty nice. This is crazy clean. For a hyperparam sweep, this is insanely clean. Still a little concerned with the learning rate. It's kind of stuck here. I mean, the only way that this thing improves at this point is to up total time steps, right? It's a little scared to like... It's kind of a little scared to increase total time steps. It should have the model correlated by now. Let's see what it does. Okay, you know, it is kind of doing it. I still think this can be made better. This thing should be able to be very aggressive right now. Hang on, maybe this is me being stupid. Wait, let me look at this. Because global search. Okay, I got a global search scale of 0.5. And Yeah, total time steps of 0.25. So total, and then, well, let me see. So like 1e8, we got like 1.5-ish. So 1e8 to 1e10 is probably going to be, I'm at like negative 0.5 to start, and then the max is 1. So you got like 1.5, and you're sampling with a scale of 0.125. Okay? So like it's going to take you a while to get up to the upper end of that range. Like it's going to take you at least 15 runs. And you're not necessarily going to sample something all the way at the edge of that scale either. So this probably just needs to get increased. There might still be some other improvements we can make though. Hold on. Because once we increase this, we don't want it to sampling really high time steps from the get-go. Yeah, this is continuing to improve, but it's slow. What next? Conservative. Let me think about this. We're waiting towards higher absolute performance. We're penalizing this by uncertainty of the performance estimates, but we're not incorporating cost in any way, right? Hang on, in what way is this thing incorporating cost? I don't think it is, right? So we have GPC. With the expected cost, we can use the Pareto value, YPF, I mean, we're barely using that one. Is this better than just using the actual Pareto point? But you could literally just use the fucking Pareto point here, couldn't you? I mean, I guess, yeah, technically, your suggestion can be higher cost. So maybe this is better. I kind of want to see how good this Pareto function is. You know? Because if this thing sucks, like, you're going to be better off just using the Pareto point. Okay, that's like a relatively small thing, though. The main thing is not taking into account cost. Like, this is uniform weighting across the Pareto front, right? This is biased to high cost. This really isn't cost aware in the way that you would think about it. Like, okay, so this is good, but it's not intelligently using cost in order to like maximize the results, the sweep result over like the result over the time of the whole sweep. It's really not. I'm trying to think how you would do that. Damn it. This is tricky. Dynamic cost penalty. Let's see. Yeah, this is very, very good. It could be faster, right? But what it's doing is very good. Has it figured out the learning rate thing at all? That one's kind of screwy. Nah, not really. Missed one parameter. Let me see. So, decreases his model cost. I don't want to penalize. I don't really want to penalize low cost or high cost runs even more than they already are. We could have an explicit exploration budget that favors using more cheap experiments early. I mean, you should get explicitly penalized based on the cost is the thing. Like, that is the correct thing to do. Information value per compute. The EI function already does that. This is difficult because it's clearly the case that you want to penalize linearly for cost. What in the hell is this? So we got base acquisition. What the fuck is that? That's like the stupidest thing ever. Oh, sans AGI. No. Literally gave me a formula with cost canceling out. Yeah, so this is what it should be. Should just be divided by cost. It should be divided by cost. Improvement times absolute performance over cost. Let me think about when you're actually going to get this. This doesn't capture the right thing. Improvement. Wait, if we have an optimal Pareto front, what happens? Hey, welcome. We are currently optimizing the heck out of carbs and fixing hyperparameter tuning in RL. It's going quite well. It was breaking my brain. This is the cleanest hyperparameter sweep I've ever seen. Yeah, it doesn't, 200 experiments though, and it doesn't upweight total time steps enough. Let me just run, since I'm doing this, let me do, I'm trying to think. Wait, no. Okay, so sample around origins in basic. This one here, right? Search distribution in basic dot sample. Normal. Okay, so what if we do this? We do uniform. And then I think, do we have to upweight this? We'll try this initially to see just what happens with the same search scale and everything. See if this works. Okay, solid. Well, we will compare this in a moment. There's going to be more work to do. I'm going to use the restroom real quick. Be right back. We'll see how this does by comparison with the uniform sampling. I actually don't know if it's going to be any better because the implicit trust region that we had is actually kind of pretty good already. Like us, we're already modulating by variance, so this might just be worse. I actually don't know. If you think about it, right, with hyperparameter optimization, do you think any web chain, blockchain, GPU stuff will be interesting? No, not at all. Blockchain maybe, Web3 is a scam. Yeah, not really at all. Blockchain tech is legit, but there's not really like, there really aren't that many uses for it if you think about it. Okay. How do I get two windows? Let me see here. I like how NYU schedules meetings on Sunday. It's funny. Enable a marketplace. Like, why? What does blockchain add to that, right? Like, in what way does it add anything? That's the thing. Like, it's like, oh, what if we do block? Like, it doesn't. Like, you can just do that without blockchain, right? Like, it doesn't make sense. I mean, yeah, you can add a crypto payment option or whatever, but that doesn't mean that the whole rest of it has to be on blockchain. That's just a payment option. So it really doesn't do very much. I don't even know if you can legally do a... What is this? I don't really want to click that. Bit tensor? Okay. I'll Google it. Guide emissions out. I don't know what that is. I don't know what that is. Is this way worse than before? I think this might be way worse than before. We'll see. That'd be interesting if it is way worse. I want to think about this here. Let's say that you have an optimal Pareto front. Different categories of subnetworks. A lot of these things you don't understand how they work because there's nothing to understand. It just doesn't make sense. Don't let me, yeah. I mean, the stuff we're doing at the moment is really freaking cool. I'm a little tired because the math is breaking my freaking head. But this is carbs. Oops, this is carbs. This is a very complicated Bayesian optimization algorithm for hyperparameter search. And I'm making it like dramatically better. So if these results, if I can finish this and these transfer well to from the synthetic task to real tasks, this will like overnight be a several-fold improvement just across the board to all of RL. Because this will let you, I mean, this will just let you get ridiculously good results out of your experiments. And to be fair, like, this is, so it's possible that I've overfit the task, right? It's possible that I've overfit the task, but so far, this is the before. Nope, not this one. This is after I've already screwed with it. Okay, so this is the before. I think I rescaled the task since then, but this is like a third of the overall possible performance. And then now, this is the cleanest hyperparameter sweep I've ever seen, and this is like 90% performance. So we're making crazy progress here. Okay, this modification seems to not be particularly good. It's still clean, but it's way slower. Maybe we'll give it a little longer. Do you need to change the search range parameter for normal versus uniform? %30 of data falls outside. Oh, it gave me two different answers, lol. I think it is 61%, right? %68 falls within one standard deviation. My probability sucks. My linear algebra is pretty good, but my stats and probability sucks. So 40% of data falls. So maybe you just need to upscale. Maybe you just need to upscale the parameter. No, I really don't know intuitively, though, which of these should be better. So you're generating 1,000 samples around a Pareto optimal point. Intuitively, would you rather do uniform sampling around the point or normal sampling? Normal sampling is going to get you more points where several of the parameters are close to their existing values and like a few parameters are different. So intuitively, I mean, that would be better for like tuning the last few stubborn parameters, probably. Whereas with uniform sampling, you get more diverse data overall, but like probably a lot of the parameters are going to be far from their initial settings. I think that normal might just be the smarter choice here. Let's see how it's fitting these parameters. So gamma's good. You know, it is kind of fitting these better though. Oh, well, this is stuck. Okay, so a lot of these parameters are stuck. Maybe you have to upweight. So this is just too slow. I'm gonna kill this and I'm gonna try to double. Yeah, I'm gonna try to double this. And if this doesn't work, then I'm gonna go back to normal because I'm gonna assume that basically the normal is better because if I double the standard deviation and it's still screwy, this should be way less stable as well. We'll see. It's kind of nice because it's like it's clipped for you. But I think I think implicitly, I already have a good mechanism of clipping. We're using a conservative estimate based on the variance of the Gaussian process. So that should prevent you from sampling way out there hyperparameters that you don't know what they're going to do. Should. I haven't actually checked how good the Gaussian processes are. Hold on. Is this immediately better? These are just random samples. So the random samples are better. We'll see if this translates to anything. I'm only going to give this like maybe 50 or so samples to do something. I'm getting hungry as well. Okay, this is actually now suddenly, that made a huge difference. To be fair, I introduced that scaling term. Before I changed the acquisition function. So now we have a way better acquisition function, so maybe we get away with larger sample ranges. I'm going to have to try this with Gaussian as well. Is there any reason I can't run these both at the same time? I think I should be able to, right? Oh, hold on. Cannot get random sample. That's interesting. That's very interesting. That was doing better as well. No candidates found. Sample search space. Sample. Oh, I see. 2 to the num dims with bounds two to the fifth Let me figure this out. It's 32. And 24. So this is generating a ton of samples. Get masked for invalid points in basic. Huh. I mean, that's interesting. So I think I know what's happening here. I think. Though it's pretty surprising. So if you have too big of a search range, then it's very likely that at least one of your parameters is going to be out of bounds. Get masked for invalid points in basic. Self.min bounds in basic. Okay. Can I just flip this? Instead of masking, samples in basic. These seem valid though. So these are all valid. It's a bit weird because you're sampling around organs in basic. I mean, this looks like this should go out of bounds to me. Search distribution in basic. There's no clipping on this. Self.search. Wait, uniform. How the fuck did this happen? Nah, wait. Uh-uh. Does this just have a weird print on it? Okay. Yeah, so this is correct. Just has a weird print string on it. Oh, I'm stupid. That's why. So this is... Oh, wait a second. This is plus... Yeah, because nothing starts at 1. Okay, cool. So this has got to be negative config global. So maybe this uniform's not that bad. Maybe I just screwed up. You know? We're going to do this for a bit. Because I don't think you should be masking these. Okay, valid sample mask. Okay, so there's some false. Valid size, shape, valid. Okay, look, there are a lot of invalid samples in there. So I think that what would be better is we do this in basic torch.clamp. And this is not it. It should be in min bounds in basic. Min. Okay. And now we no longer have this shit. And hopefully this works. Okay, cool. We'll see if this is too ridiculous. Uniform fixed one. We'll do this. So I changed this. I don't know why they do this. Because pretty much, let's say that you sample a point that's like really close to a boundary. It's a pretty good chance you just generate all invalid samples. But you should just clamp, and then you never generate invalid samples. At least that's what should happen. I mean, we're very, very quickly improving this thing here. So let's see. So this is the next run. We'll see how this compares to normal. If it's too noisy, I'll crank the standard deviation back down since I had it wrong before. Oof. Dinner in about an hour. And then however many hours I've got left in me on this tonight. This is exciting though. This is very, very good progress. Very good progress. Realistically, I think we're only a few changes away from having this algorithm solid. There are a few things I'm not fully happy with yet. So the algorithm right now needs to be biased to shorter runs, but it needs to have a mechanism to quickly scale to longer runs. Right now, it's not biased to shorter runs, but for some reason tends to do them anyways and takes forever to do longer runs. This can be improved. Maybe too noisy, we'll see. Intuitively, if you switch distributions from normal to uniform for sampling, do you need to change the size? If you're sampling with a standard deviation of 0.5 with a normal distribution, you just change that to a uniform with 0.5? I mean, like 32% of your data from the normal is going to fall outside of those bounds. But a lot of your points are going to be closer to the center. Whereas with the uniform, you're going to end up with more points not near the center, but then you're hard clipped to 0.5. I don't know. I really don't know. We'll just have to do this empirically, which is slightly annoying because, I mean, Neptune takes a couple seconds to load, and then Carbs takes a few seconds per point, which is annoying, but whatever. Better than doing full-scale experiments. Let's load this up versus the other one. So this is what we had here. I can't, there are too many points. I'm pretty damn sure this is worse. Eh, maybe not. I think you have to give it like, what, 40 points or something? Let's see. Let's just eyeball this. So around here is 50 points. Takes around 50 points to get to 2,000. Nice and stable here. Could be on track. Hard to say. These samples are pretty darn noisy, though. Pretty darn noisy. See, we would like these to be much more consistent. This could possibly be me cranking the standard deviation too high, though. We'll give it 50 points, and then I'll try again with half the standard deviation. Unless this magically improves very soon, I think this is just worse. I'll make the change preemptively, and then we'll wait until 50 to actually rerun it. So this one was at 0.5. Also, this exploration bias we gotta look at as well. I mean, this kind of works. It's noisier than before, though. Definitely noisier. So, like, here, let's just look at what this gave us, right? So this is about half, and this is about half and half. So we're gonna just go like this. This was a very smooth up to 2,000, right? Very, very smooth. Yeah, this is worse. We can kill this, and then we can try this with 0.5. This should be the closer comparison. If this isn't better, then I think normal is just better. And we can tune the normal. I guess normal intuitively, like, normal is worse if you don't have some sort of trust region, if you don't have some sort of mechanism for rejecting crazy outliers, but we have that. So normal should give you more points that like change just a few variables. It's kind of close to a local search. It's possibly better. Though I do wonder, if we look at this, now see the learning rate is still screwy even with this. And lambda is still drifted with this. So the uniform does not solve this weird drift issue. I thought it would, but it does not. Which is very weird. Okay, so We'll see if this does better. If not, I think we just stick to normal. It's very weird how much worse this is. It's like a lot worse. This is just one synthetic problem, but still. It's a lot. How is it this bad? It's kind of impressive, like, what a difference that makes. I didn't screw it up, right? Like, uniform. No, this is correct. Makes a huge difference. Holy. There's probably a ton of value in just getting the scales right for everything as well. We'll definitely have to look at that. I wouldn't be surprised as well that this synthetic problem, tuning it on this, is pretty representative of a lot of problems, because, like, the parameters are pretty close and all. I don't know how it's this much worse. It's kind of crazy. I mean, it's not like it's failing. It's definitely working. It's just what's this doing? It should be going down to 001. Okay, gamma's good. Oh, this actually looks better. These haven't been sampled at all. Possibly the search range is too small. Interesting. It's missing a lot of the scale params. It gets stuck on all of these. The normal just kind of worked. Okay, so let me think now going forward. I'm gonna think about this in the meantime. We want to downweight by cost. We want to penalize you for running high-cost experiments for no reason. What happens if your Pareto front is perfect? So if you have a perfect Pareto front, the only way to improve is by The only way to improve is by running longer experiments. Oh shit, wait, their formula's fucked. Whoa, wait, this is wrong. This is just wrong. Look, I think I found another thing. God damn it. So look, they use this whole extra Gaussian process for estimating cost, okay? And then whatever point you sample, you estimate the cost of this point. And then you take the Pareto value here, okay? And you estimate the cost of this Pareto point. So what you're doing is you're estimating the difference between the point that you've selected and your estimate of the optimal point that costs that much. And then you're taking ReLU, which, to be fair, I didn't see ReLU in the code, but then what happens here is that if your Pareto front is, if you have a perfect estimate of parameters in Pareto front, this is always 0. So you can't even improve. You're not even allowed to improve by running longer experiments under this. You're not even allowed to improve by running longer experiments because you're being compared to a hypothetical point that you haven't even obtained yet. That's terrible. Okay, let's say that we fix that, right? Then, if we have a perfect Pareto front, the only improvement will come from running a longer experiment. So this is going to be 0 for everything that is not a longer experiment. And then absolute performance is going to be like a high positive number, right? And then cost is going to downweight you. What if there's a little bit of error, right? What if there's a little bit of room to improve somewhere else on the Pareto front? You're basically going to improve everywhere first, aren't you? You're going to improve everywhere on the Pareto front before you improve at the end of it. So that might bias you towards too many short experiments. I mean, we're going to have to run it. There's just a lot of ablations to run here. Okay, this is definitely bad. So don't do this. Do normal sampling. We'll run a few of these just to make sure that we're good. And then let's replace the estimate with the Pareto point. Let's replace the estimate with the Pareto point. This should at least improve our synthetic test. We'll see what happens when we will see what happens when you have noise in the estimate. How badly that hurts you. Okay. So this is your Pareto surrogate, right? Best mu is equal to Pareto surrogate, which is not what we want. What we want is num to generate. Origins in basic is the Pareto groups. So we're gonna have to look at that. Let's make sure. Yeah, this is going well. You see, so just immediately we get our curve back. Okay. So yeah, I didn't break anything. We're good here. So, but I need to figure this one out. How to replace this. Ironically, I don't think we're going to need the cost estimate model, are we? No, we are. We're still going to need the cost estimate, but separate. Generate candidate. Why is it never calling generate candidates? Hello? Get to 15. These random points. Oh, there we go. It's weird. It took a while. I guess it's because the logging was fun. So we have samples in basic shape. Jesus. That generates way too many samples. How does this work? Wait, origin samples. Uh, origins basic. Sample around origins and basic. Wait, origin index, categorical. Ah. Okay, so that's going to be you're going to have to give it origin index. Okay. Sample search space. We're doing this in order to get the means. Do you need this? I don't know if you need this. But you definitely need index. Okay, and then what you do is go equal launch index. Okay. Origin index max groups. That's interesting. Oh, for some reason they're the same. They're resamples, the same parameter. Okay. So answer x dot plus 4. Burrito groups. Pareto groups. Did I misspell it, or is it just a stupid? All right. Let's try this. Wait. Oh, okay. I think you just have to do it 0. Let's try this. Does this run? Okay. Oh, this is incredibly stupid. This is gonna be fine. Okay, so this is good. Temp expected. Sensor device. Hold on. Origins in basic. Samples in basic. We're getting rid of this garbage. Really? Hmm. That's interesting. Does torch.clamp not actually clamp correctly? I guess the transformation is a little off. It's not good though. Try that. And actually, let's make that bound a little tighter. Okay, so now this is running. Let's see how we do. Let's see how we do. And this is going to ask me for a PI key again. I honestly did not expect to be changing carbs this much today. It's kind of insane. This is like so much algorithmic depth for one day. This is a brand new algorithm. I'm leaning towards neocarbs for a name. Oops. Let's see how this does. There are two changes here. There's the masking change, and there's the Pareto baseline change. We shall see. It's quite a fair bit of work. Is this worse than before? Let's see. Well, maybe. Are we stuck? I mean, we're going to have to test these two things separately. It could be that the clamping doesn't work. Clamping should work, though. I'd be quite surprised. 600. Let me think if there's any way that I could be wrong here. I'm pretty sure I checked the math and it doesn't make sense as is. Like, this is your expected improvement versus the Pareto front, right? If you have a perfect estimate of the Pareto front, then this is 0 everywhere, right? Even if you don't have the experiments run yet, right? That seems wrong. So, I mean, if you use the estimate of the current point instead, then you get a benefit for doing a longer run. Or you can get a benefit for doing a longer run. Because you have a weaker baseline to improve over. So this should help bias you towards longer runs as well, provided that you're confident in the parameters. Oh, hold on, here we go. Yeah, okay, it took a second. Let's see how the shape is. Okay. Whatever. Slightly different shape curve, I think. What's this, 1600? 1635? What did we have before? This one? Yeah, so in 35 is, I mean, that's like, okay, it's a pretty similar shape initially. I just wasn't looking at it. We'll see how that goes. This point is not good, but we'll see. I think it's like 2050 or something. I just want this to not hurt. You know, if it doesn't help, okay, there you go. So this total time steps is a little sketchy. Will we get up to 350, 300 something mil? Does that happen in the other one? Oh yeah, no, there's a little bump at the start. Okay, that's fine. This is such a clean curve though. Okay, yeah, that's good. I don't know what these points are doing. Are these Pareto? You got this brown one here. Oh yeah, so it was going for like a lower cost thing. Interesting. I don't know if this looks as good. Like this lambda is still drifting. Learning rate's about right, but we'll see if that drifts. Other params are looking good. I mean, this is pretty close to the original with a few outlier points, though. We're pretty close, pretty darn close to the original. I don't like these outlier points, and I don't know why they're here. Let me think if there's any good reason for them to be here. Well, actually, hold on. Yeah, they could be Okay, so you actually can get stuff like this. Um, Let me look at where can I find this? This is AB 12151. Okay, that is a Pareto point. You see? So, yeah, this is probably it's just getting rewarded for improving over a previous Pareto point that it sampled. So that is actually kind of a problem now that I think about it, because you can kind of get infinitely rewarded for running the same experiment, can't you? Which would be this cluster. Let's see if that happens in practice. I mean, this is pretty good. It's not as clean though as before. Let me think about that exploit. So the issue here is you get clusters like this because you get rewarded for running something that's like a little higher cost and does a bit better. But you get rewarded repeatedly, I think, for the same experiment. Okay. sampled sonnet, not that smart. What if we compared the predicted efficiency Yeah, this doesn't make any sense. So I mean, this is still good, but we'll see how this goes by the end. I think that you're getting rewarded too much for doing stupid shit. Like if I look at this, there's this like dense little cloud here. Does this happen with the 200 run? If I do this. Yeah, this is like a better spread Pareto front. You don't have like a little tiny cluster anywhere. This is very, very clean, and you can see there's so few points out of the front. By comparison, yeah, this front is already worse. I don't know how it gets this point. I mean, I guess technically you can literally just take any point, right? You take any Pareto point, like over here even, and you just crank it up and run it for longer. Even then, I think these are bad samples. It's weird that that matters so much. I mean, this makes sense. This is literally just like each of these points is Pareto. Well, that could actually be it, though. Like, just losing that many samples could also just screw up your prediction functions, your Gaussian processes. I mean, this is not bad, but I think it was better before. But theoretically, let me think about this. So you want to know how much better your thing is than the current optimal on that front. If you can't improve the front, you don't get anything. I don't like that it's improved the optimal. It's rough. What's the original function? So it's you take this. It's just the acquisition function originally, right? What if I did plus? plus the absolute performance. You have to get the weighting term right is the problem. To do that, that adds a weighting hyperparameter that's very difficult to tune. If you do absolute performance over cost, absolute performance over cost is going to favor shorter runs still is the problem. This is hard. So like, this is what I was looking at here. The problem is improvement. First of all, this is a conservative bound on improvement. Well, hang on. I'm no longer clamping. Yeah, I'm no longer clamping this thing, right? So even if these are all conservative bound negative, you're still going to run the best experiment out of all of these. Right? I think that I need to add a bias term to this so that this is never negative, though. I need to add a bias term so this is negative, never negative. Because otherwise it's going to get scaled weird. Okay, so I think that solves that. As long as I'm not clamping this by mistake somewhere. Am I clamping this by mistake somewhere? Okay, so here's the function. So you have the samples. This is fine. This clamp is fine. And then you get surrogate model output cast. This is max masking is fine. Expected improvement. Okay, I think the relu is not here. At least I don't see a relu anywhere, so I think I got rid of that successfully. I hope. We'll see if that can be negative. So now, let me go get the Pareto surrogate back. Let me go get the Pareto surrogate. Oops. Let's go get the Pareto surrogate back. Where is it? Get the Pareto. Pareto. Yeah, this one. So we're going to use this Pareto surrogate. And I like this wasn't terrible. This was not terrible, I don't think, right? Let me make sure that this is so 135 at 2500. Let's just make sure this is not somehow better. You know, this is about the same. We get 2500 and about 100 points here-ish. That's about the average. And time steps go up like that. Cost might be lower here, hard to say. Pareto front is messier though. I think they're pretty similar, but I like this is slightly worse, I'd say. And like theoretically, we just need a bias term is all for the cost. Hold on. Okay, I gotta go for dinner. I'd like to run something while I'm at dinner, just so I get one more experiment. I don't think that this is gonna work here. We're gonna try this, but I don't think that this works. It's conservative absolute by where's cost? We'll run this. I do not think that this works for reference. Okay, I'm gonna call that there. I'm gonna go to dinner. I'll be back in roughly an hour-ish, and we will continue working on this probably for another 2 hours. Hopefully we get this like solid. It's very close. There are just a few things that need to be improved. All the info for all this is on puffer.ai, Discord, X, GitHub, start to help